All right, well, good morning and welcome to the last class of May. We're down to just a few more weeks, so we're definitely in the home stretch here in Trig. And today we're going to start into the last chapter. Um, really, we're going to start looking at applications of Trig. We're really going to actually use this stuff the way that Trig was intended. Pretty much up to this point was just getting you comfortable with the idea of Trig and how these things work and really preparing you for later. But now we're going to actually have some fun and measure triangles and all that good stuff. So before we dive too deeply into that, any questions about what we were doing before in terms of solving equations? Any questions on that homework? Okay, so again, silence means everything is going all right. At least I'm going to assume that. Okay, so as promised, we're going to start. Oh, all right, so hold on. So Cameron just said number 3 and 5 on the video assignment. Can you tell me which section video assignment you mean? So B. All right, let me go pull it up here. Wednesday's lecture, couldn't find it on YouTube. That's a good question. I thought I had done them all. Oh, the video title is wrong. Thanks, Trayton. Oh, I had the wrong date on there. Okay. I will definitely go in there and fix that, but thank you for mentioning that. And I apologize for that error. Okay, so finally have video assignment pulling up here. So let me go ahead and share my screen so that we can all see what we're looking for. Okay, so 2 and 5, Cameron. All right. But here we go. We'll go and share screen. Okay, so everyone should see my screen here. So for number 2, it says we want to solve for the exact solutions in the interval 0 to 2 pi. And if it has none, we'll make it known. So again, your equation might not be exactly like mine, but at least should be similar. So let me go ahead and write this up on the board. And then we'll talk about how we're going to attack it. So we got 1/2 tangent squared x equals 1 minus secant of x. And while we're here, I'm also going to take a look at number 5. So number 5, we've got a similar kind of equation, but this time we've got cosines and sines. So let me just go ahead and write this one down here. We've got 12 cosine squared w plus 5 sine w minus 10 equals 0. So I don't know that I'm going to solve both of these all the way through because they are pretty similar, but we definitely will take a look at them. And then I saw that there was another question. I think Bella threw something up in here. Let me check my chat real quick. So from assignment A, number 3. Okay, let me just go ahead and backtrack to that one. Hopefully this will save us time just by finding all of these at the same time. course, that's dependent on my computer not being terribly slow. This is usually the time I ask if people have any good jokes to share. Okay, so I got one. My wife found this one the other day. All right, so why did the chicken cross the road? To get to your house. Okay, but now there's a second part to the joke. Knock, knock. The chicken, duh. Yeah, that's your good old like second grade joke of the day. All right, my computer is really not wanting to find that second assignment. So while I am pulling that up, we're gonna kind of multitask. So I'm gonna stop sharing and we'll go to the board and at least talk about these two that I was able to pull up. Okay. So hopefully you guys can see the board. Got the whiteboard up. And so these are the two equations. Let's start with this first one where we have the 1/2 tangent squared x equals 1 minus secant x. All right, so what we know is that we need to get our trig function all by itself, right? We want to be able to write something like tangent of x equals a number, or secant of x equals a number, or something along those lines. And the issue with this is that we actually have two different trig functions. We've got both the tangent and the secant. So what we'd really like to do is be able to make it so that we have only one trig function. So question for class, is there a way that we can change this so that it's all just tangent or just secant? Do you see something we could do to do that? Well, remember what we've got in our toolbox, basically, right? Thanks, Amber. Yeah, Pythagorean identity. What we want to do is make use of algebra and identities to help us out here. And here we can definitely use an identity. We know how tangent squared and secant squared are related. So what I would do is I would change this tangent squared into secant. So instead of having 1/2 tangent squared, I'm going to have 1/2 secant squared minus 1. And that secant squared minus 1, that's what you get when you solve the Pythagorean for tangent squared. And now that we're here, we're going to be able to use algebra. So I'm going to multiply by 2 to clear my fractions. So I get secant squared x minus 1 is equal to 2 minus secant x. And now I'll move everything to one side. I'll move that secant and that 2 over here to the right. So I get secant squared x plus secant of x minus 3 equals 0. Oh, whoops. Should get 2 on that secant. So we did one identity step that brought us here, and now we're going to be able to factor. This thing's a quadratic form, So if you let u equal secant, you can really see it. But I'm going to go ahead and just jump to the factoring. So this would factor as secant of x plus 3 times secant of x minus 1 equals 0. And the beauty of this is that now we can go ahead and get our secants solved. This second equation, I'm not going to solve it, so I'm going to erase it, but I'm going to talk about it in just a second. So let's finish this off. We're going to get secant of x equals minus 3 and secant of x equals 1. So that's what the secants have to equal for this to be true. And now we can find our angles. So start with the secant equaling 1. Anyone remember where that is? All right, thanks, Mariola. That is at 0. So this is going to give us x equals 0. And then, of course, we're going to put plus 2 pi n on there to be good. So there are all the places where secant is equal to 1. Okay, and then we have secant of x equals minus 3. So does anybody know where that happens? All right, so Mariola just says DNE, as does Devin. Okay, so if you look at your chart, you will see that there is no place where secant is equal to minus 3. However, there is an angle where secant is equal to minus 3. Because secant, the values we get out of secant are from 1 to infinity and from minus infinity to minus 1. So this is in the range of secant. So we're going to have to find that angle. And of course, the way we're going to do that is use our calculator. And what we'd really like to use is inverse secant. However, we don't have an inverse secant button. So let's go to cosine. Let's go to the big 3. So this guy, secant equaling minus 3, that's the same as cosine equaling minus 1/3. And now I can actually find that x by using my calculator. I can do inverse cosine of minus 1/3. So I'm going to go ahead and do that. Make sure that you're in radian mode, however, because the question did ask us for this, for angles between 0 and 2 pi. So that tells me for sure I need radians. All right, so we're going to get in the decimal approximation for this. Oh, sorry about that. And so this is around 1.91. All right, Mariola agrees with me there, 1.910633. So again, we want to be good about it. We should put a plus 2 pi in. We don't really need that for this specific question, since they're asking only the values between 0 and 2 pi. If I add or subtract 2 pi to this, I will no longer be in the right interval. Okay, but this is not the only one. Remember that when we do these inverse trig functions, that's only finding us one angle that's in the correct interval. We have to worry about the other possible places. So let me real quick, I'm going to run back up here and draw a unit circle. So here's a unit circle. And think about 1.91. I know that that's in quadrant 2. You can figure that out by just looking at how big this is compared to pi. It's less than 3.14, and it's bigger than pi over 2, which is like 1.56 something, or 1.57, I mean. Anyway, so that's in quadrant 2, but really the reason I know that is because of the inverse cosine. Inverse cosine only gives me angles between 0 and pi, so quadrants 1 and 2. And this one's in quadrant 2 because it's negative. That's where cosine is negative, is up in quadrant 2. Okay, well, anyway, the point of this is that that's the angle that we just found. But there is another place where we can actually be with a value of -1/3 for our cosine. And that's going to be in the third quadrant. I have to find this one as well. All right. Well, here's how I would do this. So we know that this angle, the first angle, the one in quadrant 2, is 1.91. So this is 1.91 whatever radians, which tells me if I go for the other direction, down to this guy, this is -1.91. So I can write this also, that x is also around -1.91 plus 2 pi n. So there are all of those. But now if we go back to the original question, the question asks us to find all the values between 0 and 2 pi that work. So let me start making my list. I know x equals 0, because that was this one over here. I also know 1.191. I don't know how many decimals you're going to need to keep, but we can keep them. And then this guy, the -1.91, it doesn't really do me any good in terms of the answers they're seeking. So I just need to find the one that's coterminal to it. So I'll just add 2 pi. So I'll take that -1.91 and add to it 2 pi. So let me see what I get here. So I get 4.3725, blah, blah, blah. So that other one, 4.37. So those would be all of the solutions to that original equation that are between 0 and 2 pi. So when you run into something like this, where we don't have a nice angle, you can still find it. We just have to use our inverse trig functions. If you have one of the non-big three, right, secant, cosecant, or cotangent, just do a real quick convert it using the reciprocal identities back to the big three, and then you can use those inverse trig functions. Okay, so I don't remember which number this was, whether it was number 2 or 5 from that section, but do we feel better about this? Does that make a little more sense? And specifically, I'm hitting this at Cameron, so he just gave me the thumbs up. Okay, so number 5, the other one with the sine and the cosine, you do exactly the same thing. You turn them into the same function using the Pythagorean, the main Pythagorean, right? So you use the sine squared plus cosine squared equals 1. You solve it for the one you want to replace and go from there. Okay, so I actually was able to pull up number 3 from the other set while we were doing this. So, but thanks for that offer, Trig. So let me go ahead and pull that up so you guys can see what it looks like. So this is another similar kind of problem where we're trying to solve an equation. It's a different equation. And let me go ahead and write up mine here. Okay, so it says give the smallest two solutions of sine of 9 theta equals -0.581. And again, it's the smallest 2 on the interval of 0 to 2 pi. All right. So again, yours may look a little bit different, but this is the same kind of idea. All right. So let me go back to the board. So I'll stop my sharing here. Okay. So we actually already have it where our sine is all by itself. So we're going to go ahead and try to get this. It's not a nice value, the negative 0.581. So what we'll do is use the calculator. So we know that 9 theta is going to equal negative 0, or sine inverse of negative 0.581. So we'll do the same thing that we did with the other problem where we use our calculator. So let me do sine inverse of negative 0.581. And I get a number of, so 9 theta is equal to negative 0.61996. I'll keep a couple of extra decimal places. But again, I need to add on to it 2 pi n. So whatever this angle is, I need to allow myself to add 2 pi n, because that will give me all of the different possible values. Okay, but this is only one of the angles. There's another place where sine is equal to negative 0.581. So let me just real quick draw the unit circle again. So here's our unit circle, and we just found the angle that's in quadrant 4. Right? It's the negative 0.61996. But sine is also negative over here. So in order to find this one, well, we have to do the whole reference angle thing, and kind of like we did before. Well, this guy, since it's negative 0.61996, that's going in this direction. The reference angle is the positive value of that. So if I want to get this angle, this is going to be pi plus 0.61996. So let me find out what that number is real quick. So I get 3.76155-ish. Okay, so let me just erase up here, because here's our other option, is that 9 theta can actually equal 3.76155 plus 2 pi n. So again, that 3.76155, that's this guy. So always find that second angle. Always look for the other place where our trig function can attain that specific value. We'll get the one using the calculator, and then the other one we have to use our reference angle. All right, well, now we can solve for theta. We just need to divide by 9. All right, we'll do that for both of these. So 9 is not confused. So we're going to get whatever they are. So let's see, that second one, I already have that stock. I've got theta equals 0.418 plus 2 pi over 9n. And then the other one, we get negative 0.688. Throw one more 8 on for good measure. 2.888 plus 2 pi n over n. So in terms of all of our solutions, here they are. But again, they asked us to figure out what were the smallest two that are in the interval 0 to 2 pi. So all you got to do there is just start listing them out. All right, so like this guy, negative 0.6888 is not in that interval. So let's add 2 pi over 9. So whatever that is, let's see. Yeah, I'll put that on my calculator here. So I get 0.629 and change. All right, so the next one, if I let n equal 1, I get 0.62947, blah, 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 blah. I'm not going to bother putting n equals 2 because I already know that this is going to be bigger than this positive number, so it's not going to be one of my first two. Similarly, if I were to take that 2 pi over n, or sorry, 2 pi over 9, and add that to the 0.418, I get like 1.1 something, which is going to be larger than this number. But that's all we got to do is just keep adding our 2 pi over 9s until we get where we need to be. All right, so hopefully that makes a little more sense. Again, I don't remember who asked that one. Oh, Bella. Is that a little bit better for you, Bella? Yep, get the thumbs up. Cool. All right, so by far, these are definitely trickier when we have to solve using our calculator, right? Because we're definitely not as comfortable with them. And what the hell is 0.418 radians mean? Well, it's an angle. It's just something we're not supremely comfortable with. But notice that the process is the same. All right, so cool. All right, well, that was a good little reminder of some of the tricks that we pull when we try to solve equations. Don't forget your identities. They're huge. And when you have extra stuff in a trig function, just solve it as if that were just x or t or whatever, and then just make sure that you replace it, find your value. Okay, so Erez, when will exam 2 be graded? I've graded almost everybody's. Yours must have been one that has not been finished. So they're coming. They're coming. Patience, patience. I appreciate the fact that you guys are really curious about how well you did. But just realize that I will get to them when I can get to them. I'm doing my best. All right. All right, so let's start solving triangles, because that's the whole point of trig, right? Trigonometry literally means triangle measurement, and it probably doesn't feel like we've done any of that this quarter. We did a very little bit when we dealt with right triangles, but today we're going to start into the how do you measure just any old random triangle. Okay, so we're going to measure some random old triangle here that's not right. It's not a right triangle. So when they're not right, we call these oblique. So if you ever see this term, oblique triangle, it just means that it's not right. All right, so because Bruce has his own language, instead of calling these oblique triangles, since they're not right, they're clearly wrong. So if you ever hear me say a wrong triangle, that's just what I mean. It's something that's not right, doesn't have a right angle. Okay, so obviously we're going to have to create some new tools because what we've got so far doesn't really help us. The trig functions themselves are perfect when we have a right triangle, but if it's oblique, then we're kind of toast. All right, well, we'll get there. But first things first, in order to solve these, you always need 3 pieces of information. And when I put here pieces of information, what I mean are either lengths of sides or sides of angles. So we're going to need to know 3 pieces of information. All right, so let's just kind of make the list of all the different things that we could know in terms of 3 pieces. So the first thing is possible is that we know the 3 sides. Right? So if you give me the 3 sides, that's 3 pieces of information. You could also give me 2 sides and 1 angle. You could give me 1 side and 2 angles. Or you could give me 3 angles. Right? No sides, all angles. So that's just the 3 different combinations, or sorry, 4 different combinations of 3 pieces of information. And yes, Amber, you're going to definitely see some stuff you saw in geometry. All right, now mathematicians, of course, we're all about shorthand and all that. So if you give me 3 sides, we're going to write that as SSS. Side, side, side. Similarly, 3 angles, that will be AAA. So then the others, where we have 2 of one and 1 of the other, there are actually 2 forms of these. So like 2 sides in an angle, we could have side, side, angle, and the other is side, angle, side. I'll explain what the difference is in these in a second. And then when we have 1 side and 2 angles, it can be kind of the same thing. It can be angle, angle, side, or angle, side, angle. So we in the math world break this into 6 different possibilities because you treat them differently depending upon which forms you have. Okay, so yay, we've got 6 of these things that we have to worry about. But let me start by helping you out, or making you happy, I should say. Of these 6, 1 of them we never do. We never ever deal with this one, and that's the 3 angles. I'm going to go ahead and cross that off because here's the deal. If I give you the 3 angle values, it's impossible to tell me how big the triangle is. Going back to Amber's geometry statement, you may remember that if you know the angles, if all the angles are the same, they're what we call similar triangles. And similar triangles are such that their side lengths are all the same ratio of each other. But you could actually have 2 triangles with the same 3 angles that are different sizes. I can actually show you that on this picture up here, this just silly triangle that I put up there. If I were to put in another line, say that's parallel to this guy, this little green triangle has the same angle values as the larger blue triangle. And so if all I did was tell you the angles, it's not enough. All right, so cool. Instead of 6 different cases, there are really only 5 that we're ever going to deal with. I don't know if you remember back when we were doing right triangles, but if you do, does anybody remember how many pieces of information you needed for right triangles? How many things did I have to tell you for you to be able to solve it? Okay, thanks, Mariola. It was 2. I could give you 2 sides, and then you could actually calculate the third side and then go from there. Or I could give you an angle on a side, and then we could use the trig values. So you might be going, oh, wow, for right triangles, you actually need less information. But that's not true, because as Sarah's just put in there, also, we have a right triangle. So we know it, we already have one of the angles is right. So in essence, we are already given one, the right triangle, and then we just needed 2 more pieces, right? So it turns out that you're always given one angle. So when we did right triangles, if I told you 2 sides, that was this one, 2 sides and an angle. If you were given an angle on the side, now you had 1 side and 2 angles, and so you were in one of those cases. Just fun fact. All right, so we're going to need to be able to develop tools that are going to take care of these. So we do have 2 rules, or 2 more cases. We call them the law of sines and the law of cosines. And those 2 are going to be able to allow us to take care of solving these wrong triangles. Okay, so one more thing I want to tell you before we dive into this is I want to give you kind of a naming scheme that we're going to use for triangles. All right, so we're always going to have 3 angles. And of course, those 3 angles are going to, they're all going to be 3 sides. Now, in terms of the way we're going to name these angles, we're going to name them alpha, beta, and gamma. So I don't know if you remember seeing gamma. I think I introduced that the first day, but just to remind you, because it may have been a while. So the sideways swimming fishy is alpha. There's the bee looking thing, curved EB is beta. And then the up and down, the downward swimming fish, this is gamma. Okay, so if you ever hear me talk about alpha, beta, or gamma, or you see those letters, that's what we're talking about. And those are the first 3 letters in the Greek alphabet. So that's why we use them in order alpha, beta, gamma. Now, the side lengths, we're going to use our letters. We're going to use English letters. And we're going to use A, B, and C. But we're always going to have them so that A is the side opposite alpha. B is always the side opposite beta. And C is always the side opposite gamma. In terms of where you put the specific angles or sides, it doesn't really matter as long as those opposites are using the same positional letter. So A always goes with alpha, B always goes with beta, and C always goes with gamma. So Eris, could you use uppercase A, B, C for angles? Absolutely. That's another thing that is common to see. I'm going to use alpha, beta, and gamma for 2 reasons. One, it's what the book uses, so that if you look back at the book, you can translate like what you see in class with what happens in the book. And the other reason is because that's how I was trained. And so I've got, well, at this point, probably 35 years worth of trig in me that makes me just go to alpha, beta, and gamma. But it's really just like anything. You can name them whatever you want, but I'm going to use this scheme always so that you always know what's what. All right, so now that we've got that, let's build our first rule that's going to help us solve these wrong triangles. All right, so we're going to build what's called the law of sines. But here's what I'm going to do. I'm going to take this triangle and I'm going to drop a perpendicular down to this side. So I'm going from angle beta, I'm going to drop it down to side B in this picture. And I'm going to go ahead and label this length as H for height. Now what I just did was I broke this into two triangles. There's the triangle that's over here on the left, highlighted purple. And then there's the triangle that's over on the right, and I'll highlight that in red. Right? But I basically just broke it into those two triangles. All right. So what I'm going to do now is I'm going to look at the sine of alpha. And the sine of alpha is going to equal H over C. So if you just look at that little purple triangle, I know two sides. I know the height, and I know this length C, which is the hypotenuse. So that's the opposite over hypotenuse, so that's my sine. And then I can do the same thing with gamma. On that side, I'm going to get the sine of gamma is equal to H over A. So I've got two equations, and I can actually combine those. And I can combine those by getting rid of the common letter. Notice that both of them have H. So let me solve one of these for H and plug it into the other. So like this one, we're going to get H is equal to C times sine of alpha. I'll go ahead and take that, fire it into the other side for H. So I get sine of gamma is equal to C times sine of alpha over A. And I'm just going to do one more thing. I'm going to move that C over onto the other side. So I get sine of gamma over C is equal to sine of alpha over A. Okay, so by dropping that perpendicular, I got this relationship. Now, the reason that I chose that one was just for the hell of it, because instead what I could have done, instead of that perpendicular, what if I had drawn in this one? Well, again, that breaks this into two triangles. Right, but now they look like this. And I could have done exactly the same thing, but using alpha and beta. And what we would have found is that sine of alpha over A was actually also equal to sine of beta over B. So if I were to cover up this piece over here, this is what we would have found using that perpendicular. If I had used the third perpendicular, which would have been this one, I would have been able to relate beta and gamma. And so I similarly would have had sine of beta over B equals sine of gamma over C. And so you notice now we're kind of like in a cycle. These things all look the same. All right, well, let me erase this extra sine of gamma over C because we already got it. But go ahead and put a box around this, because this right here is your law of sines. So it's called the law of sines because it involves the sines of these angles. But what we see is that the ratio of the side length and the sine of the angle opposite it is always the same in any triangle. All right, so this is law of sines. It's pretty easy to remember. It's not that complicated of a form, but it's really, really useful when we're trying to solve triangles. But here's what I want you to notice. In order to use this, we need to have a sine and angle pair. We need to know some sort of side and angle that are opposite each other. As long as we've got that, we can use the law of sines. All right, so let's go back to that list of the 5 different things. Remember the side, 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 the angle, side, angle, all that good stuff. And let's look at which of those the law of sines will apply. All right, so we're just going to make a list here of where we use this. So use the law of sines for, okay, so the first is going to be any 2 angles and a side. So this is going to work for angle, angle, side, and angle, side, angle. Now you may be curious what the difference is between those two because you may not have seen that before. Well, let's again draw some sort of triangle here. So the way that these work, let's say we know 2 angles. So let me go ahead and label them here. Let's say that this is alpha and beta. Those are the 2 angles we know. The angle, angle, side would be where we know these 2 angles and one of the sides that's not in between them. So if we were to know one of those 2 sides, this would be angle, angle, side. Kind of read this as going in order, either clockwise or counterclockwise, what information we have. So it would be like angle, angle, side. Or if we go the other direction, angle, angle, side. For angle, side, angle, that means that we know the side length that's between the 2 angles. So that would be angle, side, angle. All right, well, let me show you why this is going to work for either of these cases. So think about what we're going to need. Let's start with the angle, angle, side. So let's say we know this guy A. So we've got 2 angles and a side. In order to finish this out, we need to find the other 2 side lengths, which are going to be B and C, and also gamma. Well, the third angle we're going to get from the fact that we know all angles in a triangle add up to 180 degrees. And then notice that we have a side angle pair. We know A and alpha, which means in the law of sines, we know the entirety of this first fraction. And then we can use one of the other 2 pieces with their corresponding angles to find those sides. We'll do an example in just a second. Okay, so clearly, if we've got angle, angle, side, law of sines is perfect because we're given a side angle pair. Now, if we change this around so that instead of given A, we're given C. So again, these brown ones are the givens. So we've got angle, side, angle. You might say to yourself, I don't have a side angle pair because I don't know either the sides opposite alpha and beta, and I don't know the angle opposite C. but we do know the angle opposite C, because once you've got two angles, again, you can find that third one by taking them away from 180. So a real quick calculation will get us gamma, and then we've got our side angle pair. In that case, it would be C and gamma, so we would use this third piece, and then use the corresponding other parts to get the other two. Okay, so how about we do an example of each, just so you can see how the law of sines works, and you'll see how fast this can go. But real quick, before I go there, I do want to mention that there is a slightly different form that you'll see for these, and some of you may have seen it written this way. I have it written with the angles on the top. There's no reason that that has to be that way. Instead, you can flip them all over, right? Because if ratios are the same, then their reciprocals are the same. So sometimes you'll see it written with the side lengths on top and the angles on the bottom. So we'll have A over sine alpha equals B over sine beta equals C over sine beta. So either of those is fine, and I will bounce back and forth between them regularly. So don't be surprised, right? So if you ever ask the question, why did you write it flipped over? I'm going to tell you because it was a more convenient form for the time. It doesn't really matter. All right. Well, let me give you an example of one. Let's see if we can actually solve this guy. So let's say that I give you that alpha is equal to 62 degrees, beta is equal to 48 degrees, and C is equal to 52. So I just gave you two angles and a side. My question is, which of the two forms are we in? Are we in angle, angle, side, or angle, side, angle? All right, so Bella just put up angle, side, angle. Good. Yep. And Amber follows. That's definitely the case. We've got angle, side, angle. We've got the side that's between these two angles. It's a different letter. That's how we know it's angle, side, angle. So this guy is ASA. All right, so let's just think about what we're going to need. We're going to need to find A, we need to find B, and we need to find gamma. Those are the missing pieces. So you'll see me write these in pairs. I'll put next to each other the side and the angle, just so that we're always kind of aware of what we're looking for. All right, so where we should start is with the third angle. Always start there. So Erez, you said knowing whether it's AAS or ASA doesn't change the algebra. Correct. It just changes our first step, our potential first step. All right, so let's get that third angle. So I know that they all add up to 180. So if I take 62 and 48, that gives me 110, which leaves me remaining 70 degrees. So gamma is going to equal 70 degrees. And now you can see I've got my side and angle pair. I've got C and gamma. So that's enough for me to use the law of sines. All right, so the next thing I'm going to find is A. So A, I'm going to go ahead and use the A over sine alpha. I have A over sine of 62 degrees. And then I'm going to set that equal to the one that I know, which is C. I've got C is 52 and gamma is 70 degrees. So in terms of the algebra on this, it's pretty quick. It's just going to be 52 sine of 62 degrees over the sine of 70 degrees. So this is another calculator question. Make sure that you're in degree mode. All right, in degree mode, because otherwise we're going to have some problems here. All right, so what I get when I use my calculator is I get that A is approximately equal to 48.9. So we'll go ahead and put that up here, 48. All right, so then to find B, we're going to do exactly the same thing, except this time it's going to be B over the sine of 48 degrees is equal to 52 over the sine of 70. Now, I could have used A and sine alpha, but I highly recommend that you don't use anything that you calculated for a couple of reasons. One, you might have made a mistake. And if you'd made a mistake, you don't want to perpetuate that error. But even more important is this is an approximation, right? My calculator gives me not exactly 48.9. If I use an approximation, any approximation error there also gets perpetuated and can end up being a big problem. So you will see that I only use numbers that I calculate if I absolutely must. Okay, otherwise I go with information that was given. Well, this one, super easy again, just multiply by sine of 48, so we get B is equal to 52 sine of 48 over sine of 70. And again, you can go ahead and do the numbers on this, and you should get something around 41.1. So knowing angle side angle, it's super fast. All right, so this was an angle side angle, but what if instead I had given you angle side? Let me just show you how little it changes things, right? And kind of get back to Era's comment, or right, earlier Era said that it doesn't change the algebra if you're in the other case, and that's absolutely true. Because what if, let me just change this a little bit. What if I told you A is 62 degrees? Well, no, let me give you new numbers. Otherwise, it may not actually work out. But let's say I told you that I'm going to tell you that A is equal to 18, that C is 22, and gamma actually, hold on. Alpha equals 18. Gamma is equal to 32. And C is equal to 20. All right, now this situation is angle side. And you know that it's angle side because of the fact that C and gamma are given. So again, think about what we're going to need to figure out. We still need to know, well, what is A, what is B, and what is beta. So think about what your first step would be. The first step is going to be solving for beta. Once we've got these two angles, we can get our third angle quickly. Then we know we've got a side angle pair, and we would just go from there. So I'm not going to go all the way through, but let me kind of show you the nuts and bolts of this. So we've got 18 degrees and 32 degrees is 50, which leaves me a whopping 130 degrees for beta. But now, if I want to find A and B, I would have A over the sine of alpha. So A over sine of 18 is equal to C over the sine of gamma. That's enough for me to solve for A. For B, similar story. I would have B over the sine of 130. Again, is going to equal 22 over the sine of 32 degrees. And so both of these, we can go ahead and use our calculator to find. But I'll leave that for you guys. All right, so before we move away from the two angles and a side case, how are we feeling about this? You seeing how we use the law of sines? All right, getting a couple of thumbs up. Most people, most students in my experience, like the law of sines because the law of sines is pretty straightforward. It's not really that complicated, at least in terms of the algebra. Okay. Actually, while I was talking, I went ahead and did the calculations here. The numbers that you get for A and B, A is 12.8. And then B is around 31.8. So just so that when you calculate it, you can go back and look and see if you get numbers that are different, then there was some sort of an issue with putting stuff in the calculator. And hopefully that was on your end and not mine. I think we did that right. Okay, so two angles and a side, pretty easy. Find the third angle. And then once you've got that third angle, use the law of sines. All right, so the other case that this works for is one of the two sides and an angle. Okay, so this is going to be our second case. And the second case that we use the law of sines for is SSA. So let me actually make this complete. So for one, it was AAS or ASA. And then for two, now this is SSA. Okay, so this is going to be where we know two sides and one of the angles. But this is a very specific case of the two sides. So like before, when Eris said it didn't really matter whether it's ASA or AAS, while that was true, when it's two sides and an angle, it absolutely matters which one we have. But you can probably see why this is going to work for side-side angle, but it wouldn't work for side angle side. Let me real quick draw a triangle here. So here's the deal. We've got two sides. So let's say we've got these sides that are A and B. And then the angle, it has to be an angle that's not in between them. So just for the sake of having one, let's just say it's this guy, alpha. So hopefully you see why the law of sines is going to work. Because we have a side angle pair. We've got A and alpha. So we can use that fraction that involved A and sine of alpha. And then we could set it equal to, in this case, the B over sine beta. And that's going to allow us to find beta. And then once we know beta, we can get the third angle and go from there. So this is why we can use law of sines for side-side angle. However, you can probably also see then why it won't work for side angle side. Because if it was side angle side, then we know the angle in between these two. And there is no way to get C. And just in case anyone's thinking, yeah, use the Pythagorean theorem, can't use that. It's not a right triangle. So there is no way to find C, and there's definitely not a way to find one of the angles. So law of sines, though, can be used for side angle. So let me show you an example and show you how this plays out. So let's say what we've got are side lengths 39 and 25. So errors, no, you will get side angle side, but we're going to have a different tool to solve for that. All right, so let's go with this. What if I told you we've got A is equal to 39, B is equal to 25, and beta is equal to 36 degrees. So I just gave you two sides and an angle. All right, so that means that we're looking for the other side, C, and the other two angles. All right, but this is side-side angle because this side and angle pair go together. All right, so what I need then is the law of sines piece that involves B and beta. And then I also am going to want it to include the A, because that's the only other thing that I know information for. So let's write this as sine of alpha over 39 is equal to sine of 36 over 25. So this time I put the sines on top. Really, the reason for that is that's what we're solving for. I always go for what we're solving for on top. All right. So if I now want to solve this for alpha, I'm going to get sine of alpha is equal to 39 sine of 36 over 25. And what am I going to do to actually solve for alpha? Good, Amber just said the inverse. We're going to use sine inverse. So you can take your calculator, put in 39 sine of 36 degrees, right, divide by 25, and then do inverse sine of that. And I got, rounded to the nearest tenth, 66.5. So let me go ahead and put that up here for alpha. All right, so notice that this just naturally led us to find alpha. The three pieces that we knew push us to alpha. And now that we know alpha, we can find gamma. Because gamma, that's just going to be 180 minus this 66.5 and the 36, which is 77.5. Okay, so now that we have gamma, how do we find C?
Well, now you have C over sine gamma equals B over sine beta.
Good. Yeah, thanks, Hava. So we're just going to go ahead and use law of sines again. But this time, we're going to use the C with the B. So this is sort of the same situation we were in before with the previous questions, previous examples. And now we can find that C. So C is going to be 25 sine of 77.5 over sine of 36. And again, this is a calculator question. So you can go ahead and punch that in and get yourself a value. Okay, so notice what the process was. It was first find the angle that we could find, right? There was only one angle that we could find, so you got to get that. Then you can go ahead and use that angle to find the third angle, and then the third angle will allow you to find the other side. Okay, so here is the information that we just found with the side angle. All right, so I want to go back to geometry for a second. Anybody remember something funky about side angle? Okay, well, let me just sort of tell you what's what with that. So side angle, that was one of the cases where you were not guaranteed congruence. Like the whole point of all this stuff was to show triangles were congruent. Let's come back to this picture. So the whole point was to show that triangles were congruent, and side angle wasn't enough to show congruence. It was one of those funky ones that sometimes showed congruence, but wasn't actually enough. So it's definitely a special case. Now, what we're doing here means that if we have side angle, we don't necessarily know that what we just found is the only triangle. All right, let me just pause here for a second because Sarah just said, you're confused how I got 66.5 for alpha. I used my calculator and I did inverse sine of the 39 times sine of 36 divided by 25. Are you okay with the fraction that we got? Yeah, okay. So it's, let me go. So it was from, at this point, we're going to do a sine inverse. So put all this in parentheses, sine inverse. So whatever this number is, you can calculate this number and then just do inverse sine. And that's how you get alpha. Does that make sense? Okay, good, you got it now. Let me just do something here real quick, because I want to be complete here. Let me just write, this is the same then as having sine of alpha equals .916944 blah blah blah. All right, so that's what this number gave me. And then I just do inverse sine. Okay, cool. Glad we cleared up that confusion. Okay, so back to side angle. So side angle is one of the ones that actually isn't enough to show that a triangle is congruent, which means in this case, we might be screwing ourselves. This might not actually be the correct triangle. And so we get into this weird situation of there may be actually more than one. So this is what we just calculated, that is one set of information that works. That is a triangle that will have those given sides and angle. But the problem is there's a second one. So for side angle, we really got to watch out for this. It's what we call the ambiguous case. And let me show you why. So remember when we were here with our sine of alpha, the very first thing we calculated, and we got sine of alpha is 0.916944, and then we do the inverse sine of that. Okay, so we ended up getting that number of 66.5. But look back, think back to what we were doing just earlier today when we were solving equations. And remember, when we solve equations, there were actually two places that we had to search for. Well, the one that we found is the one in the first quadrant. We're expecting that. We should get one in the first quadrant since this is positive. But where else is sine positive? What other quadrant? Okay, so Bella just says 2. Yeah, quadrant 2 is another possible location. And the thing about quadrant 2 is that those angles fit in a triangle. So whenever we actually go and calculate an angle using the law of sines, we have to allow ourselves an or. Okay, so here's the deal. We found that alpha was equal to 66.5, but there's an alternative. I'm going to put here or. Alpha could have been the second quadrant angle. Well, we get the second quadrant angle by subtracting our reference angle from pi, or 180 degrees. So if you take 180 and you subtract off 66.5, you get 113.5. So that was another possibility for alpha. Now, it is possible that that second angle still won't work because it might be too large. But if you look at what we already had, we had 36 degrees. That means we still have 144 degrees that we can use for our angles. And 113.5 is plenty small.
How did we get 113.5 again?
180 minus 66.5. I'm using reference angles. So that means there's also an or for gamma. Instead of 77.5 degrees, we would take our 180 minus 36 minus 113.5. And I believe that gives me 30.5. And so that's a drastically different triangle, right? Those angles are very, very different. Well, obviously, if gamma is different, then C can be different as well. So I'm going to put here or right above it. We could also find that C is equal to 21.6. So we actually get two completely different triangles with that original information. Ugh. Okay. There's nothing we can do about this. It's just the way that this works. So let me just write this here. Side angle is what we call an ambiguous case. Ambiguous, that just means we're not really sure. So the example I just showed you showed two different solutions. We're going to see that side-side angle sometimes gives us 1, sometimes gives us none. It really just kind of depends. All right, well, we'll talk more about this next time because we kind of need to end up so you guys can go ahead and take your quiz. But real quick, because we definitely need a word of the day. The word of the day today is scissors. All right, so again, going with what's around me. I happen to have a pair of scissors nearby. So the word of today is scissors. Scissors. All right, so what we're going to be doing next time when we meet again on Monday, we will do a couple more examples of this ambiguous case, the side-side angle, and then we'll develop the law of cosines. And the law of cosines will take care of the other two cases that we don't know, the side-side-side and side angle side. Okay, so that's where we're going. That's where we'll be. So I think that's really all I have to tell you, other than expect to see your exams if you haven't gotten your exam score yet. Most of you should have seen them and gotten comments, but for those of you who have not seen it, it will be very soon when they're done. All right, so any other last minute questions before you guys go run off and do the quiz? No? Okay, so just so you know, the quiz will open up at 12:30. So in like 5 or 6 minutes. It's on sections, I think 9.3 and 9.4. It's whatever the two sections on identities are before equations. So the ones that are double angle, half angle, sum to product, product to sum, those guys. So I think it's 9.3 and 9.4. I might be off by one section there. Okay, so again, you'll have a half hour to take it and then an extra half hour to get it uploaded to me. So just make sure that it gets uploaded in by 1:30 into Canvas. All right, so any other questions before we call it a day? All right, well, seeing none, you guys have a wonderful weekend and I will see everybody on Monday.